Hello, science fans! Bill Nye here, ready to spark your curiosity. Today, we're diving headfirst into the electrifying world of circuits, the very lifeblood of modern technology. We're going to unravel some mysteries and get a grip on the fundamental principles that make our digital world tick. Every gadget you use, phones, those pocket-sized portals to the world, computers, the workhorses of the information age, lights, illuminating our homes and streets, relies on electricity flowing through circuits, a carefully orchestrated dance of electrons. It's a flow that powers our lives. But electricity, like any force of nature, faces obstacles that slow it down, influencing its path and intensity. This is called resistance, the unsung hero of circuit design. Resistance is crucial. It's not just an inconvenience. It controls how much current flows, acting as a gatekeeper for electrical energy. This control is vital, keeping devices safe and functional, preventing them from overheating or short-circuiting. Think of it like a river. Imagine the flow of water. Too much flow causes chaos, eroding the banks and creating floods, just like an electrical overload can fry your circuits. Too little and nothing works. A trickle won't power a city, and a weak current won't run your devices. Resistors manage this flow, carefully regulating the current to meet the needs of each component. This precise control is what allows us to design circuits that work just right, achieving the perfect balance of power and efficiency. Calculating total resistance is like making a blueprint for your circuit, a detailed plan that ensures everything works in harmony. It helps us predict if a light will be bright or dim, giving us the power to fine-tune the illumination, or if a motor will spin fast or slow, allowing us to control the speed and power of machines. This knowledge isn't just for engineers. It's relevant to everyone who uses electronics. It's in your dimmer switch, allowing you to set the mood with the perfect lighting, and your stereo's volume knob, giving you control over the soundscape of your life. By mastering resistance, understanding its principles and applications, you unlock the power to create and control amazing electronics, pushing the boundaries of what's possible. Let's explore the two main ways to connect resistors: the fundamental building blocks of circuit design series, where resistors line up one after another, and parallel, where they stand side by side, each offering a different path for the current to flow. First up, series circuits. Imagine holding hands in a single line. Components are connected end to end, forming one path for electricity. The current flows through each resistor in turn, with no shortcuts. It's like a one-lane road. Every car must pass every landmark. The current is the same at every point in a series circuit. Old holiday lights are a classic example. If one bulb burns out, the whole string goes dark. That's because breaking the path stops all current. Each resistor adds to the total resistance, making it harder for current to flow. Think of it as climbing one hill after another. Each adds to your total effort. This simple setup makes calculating total resistance straightforward. Here's the easy part. To find total resistance in a series circuit, just add up all the resistors. The formula is R_total equals sign, R1 plus R2 plus R3 plus, and so on. The more resistors you add, the higher the total resistance, and the lower the current for a given voltage. Imagine drinking a milkshake through several straws connected end to end. Each straw adds to the difficulty. Engineers use this principle to create precise resistance values by combining standard resistors. It's like stacking blocks to reach the exact height you need. Series connections are a simple, powerful tool in circuit design. If you can add, you can master series resistance. Let's see it in action with a real example. Let's try a real example. Suppose we have three resistors in series R1 equals sign 10 ohms, R2 equals sign 20 ohms, R3 equals sign 30 ohms. To find the total resistance, use the formula R_total equals sign R1 plus R2 plus R3. Plug in the values R_total equals sign 10 plus 20 plus 30. Add them up. 10 plus 20 equals 30, 30 plus 30 equals 60. So, the total resistance is 60 ohms. That's it. The current faces 60 ohms of opposition as it flows. This is as simple as adding up your shopping bill. Series resistance is all about straightforward addition. With this skill, you can design circuits with exactly the resistance you need. Now let's see what happens when we connect resistors in parallel. Now let's delve into the fascinating world of parallel circuits. These circuits represent a fundamental concept in electrical engineering and are essential for understanding how many electronic devices operate. We're going to explore their unique characteristics and how they differ from other types of circuits. Unlike a series circuit with just one single solitary path, parallel circuits offer multiple independent branches for the electrical current to flow through. This is a key distinction that gives parallel circuits some very useful properties. It's conceptually similar to a highway with many lanes available for cars, or perhaps a river splitting into multiple streams, each providing a separate channel for the water to flow. At each junction point, the total current splits. Each branch receives its own share of the total current, depending on its resistance. Think of it like grocery store checkout lines. More lanes mean less waiting and a smoother flow of customers. Similarly, more branches in a parallel circuit allow for more current to flow overall. Each resistor placed in parallel provides a separate path for the current, effectively reducing the overall resistance of the circuit, and all the branches eventually meet up again, converging before returning to the original power source, completing the circuit. The total current is divided among the various branches, with each branch carrying a portion of the total current. But here's a crucial point. The voltage across each branch in a parallel circuit remains constant and stays the same. Household electrical wiring is a perfect real-world example of parallel circuits in action. Each outlet receives the full voltage from the main power supply, ensuring consistent operation of your devices. And because they're wired in parallel, unplugging one electrical device doesn't affect the operation of any of the others. Now imagine for a moment if your entire house were wired in a series configuration instead of parallel. Unplugging just one single thing would immediately shut down the entire electrical system, plunging your house into darkness. Thankfully, parallel circuits are the standard, allowing everything to keep running smoothly and independently of each other. Calculating total resistance in parallel is a bit trickier. Adding a resistor in parallel actually decreases total resistance. More paths make it easier for current to flow. The formula uses reciprocals, 1/R underscore total equal sign 1/R1 plus 1/R2 plus 1/R3 plus. After adding the reciprocals, flip your answer to get R underscore total. Think of it as opening more checkout lanes. Everyone gets through faster. Each branch's easiness adds up, and the final flip gives you the total resistance. The total resistance in parallel is always less than the smallest resistor. Let's work through an example to see how it's done. Let's calculate parallel resistance with two resistors. R1 equals sign 30 ohms, R2 equals sign 60 ohms. Use the formula 1/R underscore total equals sign 1/30th plus 1/60th. Find a common denominator. 1/30th equals sign 2/60ths, so 1/60th stays the same. Add 2/60ths plus 1/60th equals sign 3/60ths. Simplify 3/60ths equals sign 1/20th. Now flip it. R underscore total equals sign 20 ohms. Notice 20 ohms is less than either 30 or 60 ohms. That's the magic of parallel circuits. More paths, less resistance. This principle is used everywhere, from home wiring to complex electronics. Remember, always flip your answer at the end. Parallel circuits make current flow easier as you add more branches. Practice this and you'll master parallel resistance in no time. Now let's compare series and parallel side by side. Let's dive into the world of circuits and compare series and parallel configurations. Understanding the differences between these two fundamental circuit types is crucial for anyone working with electronics, from hobbyists to professional engineers. We'll explore how current, voltage, and resistance behave in each type, and what the implications are for circuit design and functionality. In a series circuit, there's only one path for the current to flow. This means that all components are connected one after another, forming a single loop. Because there's only one path, the current is the same everywhere in the series circuit. No matter where you measure it, the amperage will be identical. This is a key characteristic of series circuits. Now let's consider parallel circuits. In parallel circuits, there are multiple paths or branches for the current to flow. Components are connected side by side, creating alternative routes for the electricity. This means that the total current entering a parallel circuit splits among the different branches. The amount of current flowing through each branch depends on the resistance of that branch. In a series circuit, a break anywhere in the single path stops all current flow throughout the entire circuit. If one component fails or a wire is disconnected, the whole circuit is dead. However, in a parallel circuit, if one branch is broken or a component fails, only the affected branch stops conducting current. The other branches continue to function normally. When you add resistors in series, the total resistance of the circuit increases. Each resistor adds to the overall opposition to current flow. Conversely, when you add resistors in parallel, the total resistance of the circuit decreases. This is because you're providing more paths for the current to flow, effectively reducing the overall resistance. The formula for calculating total resistance in a series circuit is straightforward. R_total = R1 plus R2 plus, where you simply add up the individual resistances. The formula for parallel resistance is a bit more complex. 1/R_total = 1/R1 plus 1/R2 plus. You need to calculate the reciprocal of each resistance, add them together, and then take the reciprocal of the result to find the total resistance. In a series circuit, the voltage supplied by the source divides among the components. The voltage drop across each component is proportional to its resistance. In a parallel circuit, each branch receives the full voltage supplied by the source. This is because each branch is directly connected to the voltage source. This is precisely why all your electrical outlets at home are wired in parallel. It ensures that each appliance receives the full voltage it needs to operate correctly, and that one faulty appliance doesn't shut down the entire house. Series circuits are simple to construct and understand, but they are less flexible and reliable than parallel circuits. Parallel circuits offer greater reliability because they allow devices to continue running even if one component or branch fails. This makes them ideal for applications where continuous operation is critical. A solid understanding of these fundamental differences between series and parallel circuits is absolutely key to designing safe and efficient electronic systems. It allows engineers to make informed decisions about circuit topology based on the specific requirements of the application. Consider using series circuits for applications where you need to control current flow precisely, and parallel circuits for applications where reliability and independent operation are paramount. Now that you understand the key differences between series and parallel circuits, you're well equipped to choose the right setup for virtually any circuit design challenge you might encounter. We've seen that resistance is fundamental to electronics. In series, add resistors for more opposition. In parallel, add paths to lower resistance. Series is simple addition. Parallel uses reciprocals and always lowers total resistance. These two setups are the building blocks of all electronic circuits. From flashlights to supercomputers, engineers use series and parallel to control current and voltage. Practice calculating resistance in both types of circuits. The more you practice, the more intuitive it becomes. Soon, you'll spot series and parallel everywhere in daily life. Stay curious, keep experimenting, and remember, science is all around us. Now go get calculating.
We'll be looking at some key differences between a circuit in series and a circuit in parallel. Let's start with an example of a circuit in series. In this example, we have a battery that's connected to 3 light bulbs. Each light bulb in this circuit is connected end to end. If we imagine a single charge passing through this circuit, we can see that it would pass through every single part or light bulb in this circuit. This is a characteristic of series circuits. Now, if we compare this to a circuit of all of the same components but connected in parallel, we can see a key difference. Let's imagine that same single charge passing through this parallel circuit. That single charge will only pass through one branch or one of our bulbs in our parallel circuit each time it passes through the circuit. In our example parallel circuit, each bulb has its own branch or connection to the voltage source or battery. Whereas in the series circuit, all of our bulbs were connected together and had the same connection to our battery. It's also important to note that how each of these components are connected to each other changes the overall or total resistance in our circuit. If we were to run an experiment on our series circuit and added more and more light bulbs to that circuit, we would see a change in the brightness of our bulbs. The more bulbs we add to that series circuit, the dimmer they all become. This highlights the fact that as we add more bulbs to our circuit, we're increasing the total resistance of that circuit. This causes the total current in our circuit to decrease. This can be stated another way. As the resistance increases in a series circuit, the overall current decreases. We can see this relationship in Ohm's law, which states that the voltage is equal to the current times the resistance, or V equals I times R. After we isolate the I, or the current, in this equation, we can see that as we increase the resistance in a circuit, we decrease the current. In order to determine the total resistance of a series circuit, we simply add all of the resistance values to each other. For example, in our circuit, if two of the bulbs have a resistance of 8 ohms and one has a resistance of 2 ohms, we would simply add 8 ohms plus 8 ohms plus 2 ohms. This gives us a total resistance of 18 ohms for our series circuit. Another key thing to note about a series circuit is if we remove any one of the bulbs, the entire circuit goes dead. The electrical current can no longer flow if one of the components is missing. If all of the appliances in your kitchen, your refrigerator, your oven, your microwave, and even the lights were attached in series, then if any one of them were turned off, none of them would work. So in the case of having a series circuit in your kitchen, to run your refrigerator, you would have to have the lights on, and you would have to have the oven on, and you would have to have the microwave on. So clearly, a series circuit is not what we have in our homes. Let's now look at the resistance in a parallel circuit. Again, if we follow that single charge as it moves around our example parallel circuit, we can see that it has multiple paths or multiple ways it can move around the circuit. And each single charge will only pass through one bulb on its way around the path. Parallel circuits have an unexpected feature, that as we add more and more resistors in parallel, we actually increase the overall current in that circuit. Because of Ohm's law, the same is also true that as we add more and more resistors, we're actually decreasing the total resistance for that circuit. Let's take a look at how we calculate total resistance in a parallel circuit. To calculate the total resistance in a parallel circuit, we add the reciprocal of the resistance of each resistor, and then we take the reciprocal of that total. This can be shown in the following equation. So let's calculate the total resistance of our initial parallel circuit. If we assume that we have the same resistors in our parallel circuit as we did in our series circuit, we will add 1 over 8 ohms plus 1 over 8 ohms plus 1 over 2 ohms. And then we will take the reciprocal of that value. This gives us a total resistance value of our parallel circuit of 2 ohms. This is a major difference in the overall resistance as compared to our series circuit, which had a resistance of 18 ohms. So as we can see, as we add more and more resistors to our parallel circuit, we actually decrease the total resistance of that circuit and therefore increase the overall current in that circuit. A final and very important feature of our parallel circuit is that if we remove any of our single bulbs, all of the other bulbs will continue to stay lit. If we apply this to the same analogy of our kitchen, it means that we can run any one of those appliances by itself, whether or not the others are on or off. Clearly, parallel circuits are what we have in our homes.